Okay, hello everyone. Hopefully this is working. It says it is. My name is Marley, of course. I'm the astronomer here at the H.R. MacMillan Space Center. And today I am joined by our guest, Miho Wakai. Hi, Miho. Thank you so much for joining
Hello.
us.
Hi, Marley.
Hello. Miho was actually here last week at our in-house at our Tanabata festival that we did on Friday, which went really, really well. And Miho is a PhD candidate at the University of British Columbia, and she studies some pretty interesting stuff, some dark matter stuff that we'll be able to get into in just a minute. But Miho was also at the Powell Street Festival, and I wanted to ask you about that. How did that go just this past Saturday?
Yeah, it was so much fun. It was actually my first time at the Paul Street Festival, and so everything was new for me, but there were so many people. So what we did was, so the HR MacMillan Space Center brought their portable planetariums. It's kind of like this massive tent, and we had like 25 people. We did 3 shows, and there was a lot of children, and we got to talk to the public about the folklore of Tanabata, which is the star festival that happens in Japan. So that was a lot of fun. I really, really enjoyed it.
No, it was fun. The in-house event on the Friday was very fun. I'm glad Powell Street
Yeah,
Festival was also
yeah.
fun because I missed that one unfortunately. But when we were in house with you here in our planetarium, we didn't get a chance. Well, we got into it a little bit, but we didn't get to do a deep dive into your research and what it is that you do, which is why we asked you to come back for Ask an Astronomer so we could talk a little bit more about your research and all of the fun things that you get to do. So I'll hand it over to you now. I know you have some slides prepared to kind of talk about it. And of course, for people
Yeah.
watching, if you have any questions, feel free to put them into the chat, both on Facebook and on YouTube. I should be able to see all of them. Again, Michael usually does this, and he couldn't be here today. So this is fun for me.
Well, you're a great host. So you're doing amazing. I think you can see this. You see this now?
I can see it. Yep, I think it's good.
Yeah. Well, first of all, thank you so much for having me, Marley. And as Marley introduced me, I'm doing my PhD at UBC. My name is Miho, and I'm going to be talking about dark matter searches in a particle physics experiment. So I work on something called Belle II. So I'm going to be talking a little bit about dark matter as well as particle physics. So let's hop right into it. So dark matter, it's this like mysterious thing, but in order to describe the story, I need to take you back to 1933, where Swiss astronomer Fritz Zwicky was observing the sky. So this is Fritz Zwicky in the photo here, and he was looking at something called the Coma cluster in the sky. Now, the Coma cluster is a photo, there's a photo of this here on the slide, and it's just sort of a cluster of galaxies and stars, all gravitationally bound together. Now, what Fritz Zwicky was trying to do was that he was looking at the different galaxies within, and he was trying to figure out how much these objects weigh, so what their mass was. Now, there's 2 different ways that you can calculate the mass. One way is to look at its luminosity, so the light that's coming out of this object, you can try and take light and calculate the mass. Now, the other way is looking at its rotational speed. So these galaxies are sort of rotating around. And if you look at the orbital speed, you can actually find the mass that way. And what he kind of figured out was that using these 2 different methods, he found out that the masses between the 2 were really, really different, even though he was studying the same exact object. And what he further realized was that these objects were moving a lot faster than what he expected. And so he thought, well, if these things are rotating at this speed, then there must be some extra mass that we can't see. Otherwise, it would be way too light for these objects to be spinning around. And so they would kind of be sucked in by the gravitational pull of the cluster. And so this sort of missing mass that he knows that it's there, but he can't see, we call this, he named it dark matter. And dark because it doesn't interact with light at all, so we can't actually observe it. So this is kind of the beginning of where dark matter was termed. And it's this mysterious matter, we know exists, but can't quite see. Now, on to the 1960s and 70s, astronomers Vera Rubin and Kent Ford were these 2 people that also observed something quite peculiar. So for them, they were looking at something, they were looking at galaxy, and they were looking at the different stars within the galaxy. Now, our gravitational laws tell us that, let's say that you're at the center of the galaxy, the further away you are from the center, your rotational sort of velocity should kind of go down, decrease. That's because your gravitational force is going to be smaller.
That's kind of like
And
how it works in our solar system, right? Like the
yeah,
planets closer to
exactly.
the sun spin much faster than the planets further out. So the idea is that
Exactly.
this would happen with the stars in a galaxy as well, right?
Right. So what they were expecting though was that, okay, like this is what we expect, and this is kind of the dotted curve in this picture here in the graph. But what they observed was that actually, okay, take all of these rotational speeds and plot them as a function of the distance further away they are from the center. And they realized that that curve was actually very different, and we call this the flat rotation curve. And they realized, well, this isn't what we were expecting. And so this meant for them is that there must be some other extra mass for this these stars to be orbiting at the speed that we see. Otherwise, it wouldn't be in this sort of stable orbit. So again, this observation told us, okay, there must be some extra mass, but we can't see it. And again, this points to dark matter. Now, this was back in the 1970s, and since then, we've actually made a lot of other observations that kind of point to the idea of dark matter. So one of them is called gravitational lensing. Now, on this image here on the left-hand side, we have Earth that we're on, and then there's this very far away galaxy. Now, this galaxy at the end is sort of emitting a lot of light, and all of this light is sort of going in different directions. Now, between the galaxy and Earth, there's this massive object in the middle. Now, Newton's gravity law tells us that these massive objects, these big things, can actually warp space-time. What this means is that the light coming from this other galaxy, that light can actually be bent by these massive objects in the middle. So what happens is, even though all of this light is traveling away from this galaxy, that light is now sort of beamed towards us because of this massive object in the middle. Astronomers like to kind of say that gravitational lensing is sort of a, what is it called? The magnifying scope? Like
magnifying glass.
Magnifying glass, that's it. Because it kind of beams more light towards us. So there's two things that this gravitational lensing effect kind of tells us. One, there is this big source of light. There's this galaxy that's very far away, and we wouldn't see it if it weren't for this gravitational lensing effect. But now all of this light is sort of amplified towards us. And the second thing is that there is some massive object in the middle between us and the galaxy. Now, all of these massive objects, it sort of tells us, okay, there's something big in the middle. And this is how astronomers can actually map where dark matter is as well, because dark matter is sort of this something massive in the middle that we can't quite see, but we can indirectly observe it by gravitational lensing. So the picture on the right kind of tells you these sort of warped lines here. And this is exactly the effect of gravitational lensing, where light is sort of being bent and being towards us. And in the middle of that is where dark matter lies. So yeah, this is kind of an additional indirect way of locating where dark matter is.
So just to like clarify, I guess, so the galaxy clusters themselves, they will also, like the stars and everything that make up these large galaxies and the clusters of them, they'll also bend the light, right? And
yes,
so we can kind of guess how much that light can be bent based on what we see in the galaxy. But then the additional dark matter manipulates the light more than we expect. Is that kind of what's happening? Okay.
I think that's what it is, yeah. So you're like the warpness is kind of what like it kind of tells us, okay, there must be some more things to it.
Okay, interesting. And because we can't see it, we have to rely on how that light gets warped for us to know how much dark matter is in that spot.
Exactly. It's sort of this indirect way of seeing where dark matter is. Yeah, because it doesn't interact with light directly, so you can't actually see it in the traditional sense.
Yeah.
So on to the next observation called the bullet cluster. Now, a bullet cluster is when you have two big galaxy clusters. So these are clusters of all these massive objects, And these two collide at a very high speed. So this is what's happening in the image here, where this is kind of the aftermath of two galaxy colliders going through each other. So on the right hand, you have a smaller galaxy cluster, and on the right, you have a much bigger galaxy cluster. Now, when these two galaxy clusters collide, most of it is just sort of space, right? So they just kind of pass through each other. But each of these galaxy clusters have a lot of hot gas. They carry a lot of hot gas. And so when they collide through, all of this hot gas sort of interacts in the middle. And this is actually what we're seeing here in pink. So this hot gas emits X-rays, and so we can actually observe it using an X-ray telescope. And this is kind of what also visible matter is, because we can actually sort of see it. And you can actually even see this sort of triangular hot gas shape from the smaller galaxy cluster where the gas is sort of puncturing through. Now, what's really interesting is that if you apply gravitational lensing, like what we just explained previously, you'll actually see that most of the matter is in the blue region, these sort of blue blobs on the sides. And this is really interesting because it tells us, well, you see visible matter in the middle, but dark matter on the sides. And this is a very clear case where dark matter and visible matter interact really, really differently because there's in these two very separate regions. So this is kind of like a very nice illustration of, well, we see dark matter and it's kind of very different from what we expect from visible matter. So now we've kind of sort of talked about all of the galaxy clusters and the big things in the universe, but I'm actually going to bring you back to the smallest of the smallest things, because I actually work in a field called particle physics. So kind of like an intro to particle physics is the standard model of particle physics. And I promise I will come back to dark matter in a second. So we have, here is the standard model. Now, this is this theory that encapsulates all of the fundamental particles in the universe. Now, fundamental particle means that it's basically the smallest of the smallest things in the universe. It's the building blocks of what we're made out of. So you might have heard the term proton. A proton is actually, it's made out of quarks, which are in the purple here. So we have, it's this like beautiful theory that has all of these different particles, and it also tells us how these particles interact. And what you're seeing here in the standard model is actually what they've all been experimentally observed. And this is what particle physics is. We try to study these particles. But the question is, well, where is dark matter? Because dark matter isn't included in the standard model. And as people in particle physics, as we particle physicists, we like to believe that dark matter is made out of some type of particle. And the standard model doesn't quite describe it. So we want to figure out, well, what is it? What can it be? And well, what can it be? It can be a whole bunch of things. And so here's kind of an image of an idea of what dark matter can be. These are sort of candidates of what it could be made out of. And you have here all of these like very funky names, and we just we're not quite certain what the dark matter particle could be. And there's a lot of experiments that are working on trying to find these different types of particles. And yeah, my experiment is also one of them. So I'm going to kind of explain what our experiment does.
I love the name Little Higgs and then Littlest Higgs. That's a very classic, very classic astronomy physics naming convention.
We have all of the acronyms. It's so much fun.
Oh yeah.
So I'm going to take you to my experiment. So my experiment is called the Belle II experiment. We are located in Tsukuba, Japan. This is about an hour and a half away from Tokyo City. It's a very big collaboration, meaning that we have about 1,000 researchers working from over 100 institutes, and these institutes are from 26 different countries. So we're a really big group very diverse group of people. Now, we started operating in 2018, so it's been about like 5 years since we started collecting data. Now, what does our experiment look like? Well, it's a collider experiment. So here on the right, I have a picture of what a collider is. A collider is called Super KKB Collider. This whole setup is placed deep underground in the city of Tsukuba. And the sort of main system where you have these rings the circumference is about 3 kilometers long. So it's a very huge setup that is located underground. Now, what we collide is, here you can see the electron ring and the positron ring in the image here. So we collide these 2 types of particles called electron and positron. We accelerate them at a very high speed, and then we collide them together. And when you collide these 2 particles, an interaction happens, so we can produce something else. And that's what we try to capture using our detector.
Exactly is a positron? Sorry, just to jump in, but what exactly is that? Yeah.
So electrons, the positron is electrons antimatter pair. So it's basically kind of like a cut and copy piece of electron, but it has a positive charge. It also has it's opposite in terms of, like, if you really want to get deep into it, quantum numbers. But yeah, it's this antimatter pair.
So it has like the same mass. It's an electron, except it's
exactly.
just positively charged.
Yeah.
Yes.
Think of it that way. So yeah, we collide these 2 particles together, and then we see what comes out. The key kind of thing about our experiment is that we have the world record for the highest instantaneous luminosity. Very big words. What this means is that our experiment is really good at colliding these 2 types of particles. We bunch them up, actually, and then collide them at a really high rate, high frequency. So what happens is that you can actually get more collisions, and then you get more data. So our experiment is very good at that. And it's sort of the engineering is sort of the world best.
We just had a question come in asking, is this the same type of collider that exists at UBC? I think that's the Triumph lab. Is it the same? Is it similar? Yeah.
That's a little bit different. That is, what they have is a cyclotron. So the mechanics are a little bit different. The engineering is also a little bit different there. It is sort of they accelerate a type of particle, and then I think what their main thing is, I should really know this, is that they actually have different targets, and they accelerate these beams of particles, and then they create, I think, the target some shielding, and then they can produce particles. The really cool thing about Triumph is that they actually capture some of these particles that they create, and I think can be used in medical facilities. Things like that. Triumph is amazing. Our experiment runs on I believe we have a higher energy. And then, like, the motivation for our experiment is a little bit different between Triumph.
Yeah.
We are much more similar to the one that's located at CERN, where it's underground in Switzerland and France, and that's kind of more comparable.
So it's closer to the LHC, right? The Hadron Collider. Than it is to Triumph. Different motivations.
Yeah, the term that you're looking for is a synchrotron versus a cyclotron.
Okay.
But yeah. Great question though, and I should probably look it up myself about Triumph.
No, that's okay. I also didn't know. I was like, I think it's different, but I couldn't tell you how exactly it's different, but it is different. Yeah.
So yes, okay. So moving on. This is the detector that I kind of talked about. So here, when you have the electrons and positrons colliding, you produce something, and we want to capture that. So we sort of wrap around in the middle of where things are colliding. We wrap it around with our detector. So here you're seeing sort of a cross-sectional view of what the detector looks like. It's 8 meters tall, 8 meters wide, 1,400 tons. So it's a huge, huge detector. And you can kind of see in the image here, it's sort of like an onion layered shape. So there's different types of parts of the detector that kind of do different things. So yeah, this is kind of the detector. And what does the detector see? Well, something like this. So here are the images that were inside the detector, and you can see what's happening. So the green line here indicates in the middle is where the electrons and positrons are coming in. And in the middle of that picture is where this collision is happening, and it's producing a lot of particles. The blues and the pink lines are sort of the particles that we're producing. And some of these are sort of curved, and that's because we have a magnetic field around the detector. And so if they have some like a magnetic charge with them, then they're sort of influenced by the field. So yeah, this is kind of what we see. So now that we talked a little bit about particle physics, I'm gonna take a step back to dark matter and see where all of this is now coming together. We're combining these things. So this is gonna get a little bit technical, I apologize, but I want to introduce you to dark sector. And this is what we as a team do in our Belle II experiment. So there's all these different ideas of what dark matter could be. But one of them is we have a theory called the dark sector theory. Now, what this does is that you have this dark matter particles, and you have the standard model particles that we know exist and we have observed. And the dark sector theory can kind of introduce this like new force. It's called the dark force. It's very Star Wars-like. And by introducing this new force, you can actually kind of communicate. So you can create a portal between the dark matter particles and the standard matter particles, and kind of creates this bridge between the two. So this is kind of what the image you're seeing here. You have this mysterious dark matter and standard model, and you try to connect them to. But what's very cool about this dark sector theory is that by introducing this, you actually get like a whole bunch of particles instead. You get like a family of particles. So you can kind of imagine it to be the dark matter version of the standard model in this theory. So in our experiment, rather than just looking for one particular thing, there's different groups looking for different particles within this so-called dark sector theory. I hope that makes sense. So specifically now really digging a little bit deeper here, what I work on is within this theory of dark sector, I look at something called the dark shower. Again, fun names here.
The dark shower. So
the dark shower.
The problem comes from the fact that the dark matter particle doesn't fit with the standard model of physics as we have right now.
There's people have different theories to describe dark matter, and we think that it's not just one type of particle. Okay,
so your experiment thinks that it's this family of particles called the dark sector is what you've named these families of particles. Okay, and you're specifically looking at this family of particles, but a specific part of it called the dark shower.
Exactly.
Okay, so all of those are dark matter. All those particles working together in the dark sector.
It's within like the realm of dark matter, if that makes sense.
Okay. So dark matter isn't just one thing. You're trying to explain it by looking at this family of particles called the dark sector.
Yeah.
Okay. I follow along now. And you're specifically looking at a dark shower.
I'm looking at a production, let's say, like you have so here we have the image here, right? Where this is what I'm trying to look for. You have the electron and positron colliding on the left-hand side. And then what it does is create a shower of particles. This is why we call it the dark shower. And all of these are sort of mostly invisible because dark matter is invisible to us. We can't actually see them. But we also need to see something in our detector because we can't just say we've seen nothing, therefore we detect the dark matter. So hopefully the idea is that one of these particles can actually talk to the normal matter particle. So this is what you're seeing here on the side where you have this rho particle. It's called a dark rho. And they can actually talk to something. And so they can, this is kind of described as a decay. So this dark rho kind of decays into something. It could be sort of like an electron or a positron. And so that's what I'm trying to see. So even though dark matter itself is invisible, I can see it talking to a normal normal matter particle. And what's kind of so special about this is that this search that I'm looking for, I want to see something particular, is unique because it's something called displaced vertex search. So what this means is we have here on our image, we have a cross section of our detector. So you can kind of imagine that the electron is going into our screen, the positron is coming out of our screen, and we're looking at sort of that cross section image. So in the middle, they're colliding and they're producing these showers of particles, right? So these dotted lines are all the particles that we're producing that are completely invisible to us. Now, the dark row, what happens, this very special particle, it lives a little bit, and then it decays, and then it kind of decays into something else that we can see. So where it decayed, where it interacted with the electron and positron is away from where the electron and positrons were colliding. So this is why we call it sort of a displaced vertex, because these two places are different. Now, what's special is that normally everything happens at the collision point. So this is why it's kind of special. It's a unique search in that way, because rather than seeing everything happening at where the collision point is, there's something happening away from it, if that makes sense.
No, I think it does. Like, so when you're colliding these electrons and positrons inside of Belle II, they collide in one spot and everything happens very quickly after that, like almost instantaneous, right? When the collision happens, you would have all these particles released. You'd have some on the curved paths with the magnetic or some sort of electromagnetic charge to them. So they're being curved out of the way with the magnetic field running along the detector. But when you're looking for the dark shower, I guess is what we're calling it, that row particle that looks like a P. Sorry for people who don't know the Greek alphabet. No, looks like the letter P. When that's produced by the collision, right, is what you're thinking is happening. And that so your electron and a positron collide, they produce this row particle, which then lives for a little bit, which is what's odd. We expect it to decay almost instantaneously, like the rest of our normal particles do. But this dark sector particle, was that what you would call it? Yeah. Okay. It lives for a little bit and then it decays, which is then it decays. Okay. So you're looking for these new electrons and positrons showing up away from the collision point.
Yes.
Okay.
Exactly. Yeah.
Because you wouldn't be able to see the row particle if it's a dark matter particle, right? Yeah.
Exactly. We can't actually see it, but we can see it indirectly from that way.
You can see the result of it decaying.
Result of it. Exactly.
Oh, interesting. Okay.
Yeah. You wrapped it up way better than I did. So
no, it's great. Just I probably should have refreshed my particle physics before doing this. It's been a while.
This is like really deep into it. I do apologize for people that came in for astronomy. I think this is maybe way too much particle physics.
No, it's very interesting because you're using something that is so small to explain something that has like galactic large impacts, right? Like it's still astronomy. It's just like our method of explaining astronomy is physics. That's all that is.
Yeah, I think that's a really cool thing is that like you have all of these, as you explain, all these like massive observations of massive things, but then we can still talk to astronomers and like learn about what are the observations and how do we particle physicists have like come in. So yeah, we kind of went through like two completely polar opposite scales of things just within this talk.
That's amazing.
But yeah, this is kind of what we do. I will wrap up. I promise, and I'll stop talking. But to conclude, the Belle II is an extremely big collaboration, and this is a photo of our collaboration meeting. The sad joke is that only my eyebrows made it to the photo, and I'm sort of a walking meme in our group now. But I love being part of a big collaboration and just learning from everyone. I really do enjoy being part of our experiment, and this is also kind of what our experiment looks like. It's when it's being repaired, that's what our detector looks like. And yeah, I just have to leave with one note that I think we have to figure out what dark matter is. That's just in my personal belief. And I'm really interested. I just hope before I die, someone figures it out.
I'm sure someone will, and maybe it'll be you. Maybe you'll find your particle decay. That'd be pretty sweet.
That would be pretty sweet. Yeah.
Amazing. Well, thank you so much, Miho, for sharing and explaining all of that to everyone. I'm definitely going to read more about it, I think, and refresh my brain on particle physics, as it's been a very long time since I've studied it. We have reached the half hour, which is great because that was, I think, a little more exciting than hearing me talk about the Perseid meteor shower. At least I enjoyed that a lot more. But for people who are interested in the Perseid meteor shower that is coming up, the peak is actually on the evening of the 12th and the morning of the 13th of August, right? It's a yearly meteor shower, tends to be around that date. And we are doing another takeover event. So just like with Tanabata, we took over the one of the time slots we have on Friday evenings. We're doing that again this Friday with a show all about the Perseids. So you can come and learn about them and learn a little bit about asteroids. Surprisingly, meteor showers their parent objects of what causes the meteor showers are very fascinating, and you can learn a lot of interesting science about them, about the early bits of our solar system. So feel free to come on down, check out our website. I think there's also a blog post that's gone out about the Perseid meteor shower you can check out instead of hearing me rambling about them. But thank you so much for joining us. We'll be back in 2 weeks talking about something fascinating, I'm sure. I just don't remember what it is yet. And thank you, Miho, for joining us again. It was great to have you. Thank you so much for coming twice, doing the event in-house and also now doing an event online with us. It was very fun to get to know you.
Thank you for having me.
Amazing. Okay, well, until next time, when Michael will be back.